So my name is Gajinder Panesar, and this is Iain Robertson. So we're going to do a two-man show. We're for a company called UltraSoC based in Cambridge in the UK. Title of the talk is Every Cycle Counts. So this is the agenda, running order. So I'll start. To me, it's not about the ISA. It's not about the core. Today, it's about understanding, getting systems to work as they were designed to work. And in order to do that, understanding complex systems is hard, very hard. And surprisingly, sometimes software doesn't work, and nobody knows what's going on. Software, I read an article recently, which was written in 2002, and it said software development costs are between 50 and 75% of the development cost in debugging. And this is exacerbated in more and more complex systems and in real time where safety and security is paramount. And in such systems, what we need is non-intrusive visibility. And processor branch trace only gives you so much. For real-time safety critical and security critical systems, understanding CPU stalling behavior is key. CPU trace can obviously generate a large amount of trace, and so managing and controlling how much you get off is important. So having different kinds of tracing, filtering mechanisms, both from within the CPU and also external events that are detected within the SoC is crucial. So I'm going to pass over to Iain.
Hi, yes. So as Gaj said, processor trace tells you, what the execution path of the program was. Sometimes that in itself is not enough. You actually want to know on a cycle-by-cycle basis when instructions were retired and when there were stalls, so you can really get the last performance out of your system. So I'm going to talk a little bit about how we achieve cycle-accurate trace, and the particular form of cycle-accurate trace that we have is we call retirement delta trace. So basically, the objective is to be able to identify on a cycle-by-cycle basis whether the CPU's retiring instructions or stalling. And so for that, you want to report the amount of time between each instruction retirement. But in fact, CPUs are pretty good at executing instructions. In practice, they'll retire instructions on most cycles with occasional stalls. So a more efficient way of representing the information is to record the number of back-to-back cycles on which the CPU retired an instruction, followed by the number of cycles on which it's stalled. And so that pair of numbers, in conjunction with the existing instruction trace, can be used to identify exactly where the CPUs are retiring instructions and when they're stalling. And for superscalar multi-issue CPUs, you also want to be able to know potentially how many instructions were retired in a given cycle. So the key to this is having an efficient representation for these sequences of numbers. So we investigated various variable length encoding schemes. So you only really use as few bits as you need to encode the values. And we looked at a number of different schemes. In fact, we settled on the Elias gamma code. There's a related code from the same person called Elias delta, which is actually more efficient over all numbers. So as the numbers get larger, it becomes more efficient. But for numbers of 32 or less, Elias gamma is as efficient or better. And for trace, if we're recording small numbers, then there's going to be a higher volume of trace generated, so improved efficiency for small numbers is more important, and so it gives the efficiency where it matters. So we settled on using Elias gamma encoding. Another feature we added to our mechanism is something we call stall amortization, and I'll talk about that in more detail on the next few slides, but essentially allows you to treat short stalls in the same way as retiring instructions, so it's an efficiency versus accuracy trade-off. Okay, so I just wanted to touch briefly on the relationship between a CPU core and a trace encoder. So on this slide, you can see the mandatory signals in the interface between the two. There are some additional optional signals as well, but these are the mandatory ones. And for cycle accurate trace, you don't need any extra information, although for multi-retirement, multi-issue CPUs, there is a performance efficiency gain that can be achieved by adding an additional signal which reports the number of instructions that retire in a cycle. The standard signaling for a multi-issue is to report the number of half words of instructions to cover, so it supports both the regular and compressed instructions. And you can do cycle accurate trace with that, but you're counting half words instead of instructions, and so the count values are larger, the efficiency is lower. But so this is an optional enhancement to improve the efficiency. Okay, so I talked about pairs of numbers. In fact, in our encoder we have 5 different number or count tokens that we call them, and imaginatively called token A, B, C, D, and E. And I'm not going to go into the details of how they're defined just here. I've got some examples on upcoming slides, which I think will make it clearer. But basically, those tokens they get grouped together into one of 3 formats. And in fact, so the first 2 formats, the A and C pair and the ABC triplet, are both runtime selectable on CPUs that retire 1 instruction per cycle. And then the ABC triplet and the DE pair are selectable on multi-retirement CPUs. And again, we'll see why, how that works over the coming slides. Okay, so I think the best way to describe and explain this is to use an example. So what I've got here is a sequence of, it represents 16 clock cycles. And with each clock cycle I've marked in green those cycles where an instruction is retired, and in orange the cycles where there's a stall. And so this is the I guess the basic format. It's for a single retirement CPU using packed groups of AC tokens. So if we look at the first group, we see how this works. So in this first group we have 4 cycles, consecutive cycles where instructions retired, followed by a single stall. So A represents the number of cycles on which instructions retired consecutively, so that's 4. And then we have a single cycle stall, which is represented in C. And then you follow the same pattern for the other groups. You see in group 3 we have 2 instructions retired, followed by 4 stalls. Below those in brackets, I've shown the number of bits required when you translate those into Elias gamma codes. So that's 3 groups, 18 bits in total, which in this example is 2 bits per instruction. Now, obviously, the efficiency there, it will vary according to the particular pattern, and in most cases I would expect higher numbers of consecutive cycles where instructions retiring, and the efficiency would be much higher for those. But it's just for illustration purposes. So let's have a look at, can we do better than 2 instructions, 2 bits per instruction? So this shows how the stall amortization comes into play. So let's say, well, we're interested in where the large stalls are, but the odd cycle here or there where we don't retire, when we were not so bothered about knowing exactly where they occur. So let's say we set in this example, I've set the threshold, stall amortization threshold to 1. So single cycle stalls will be treated the same way as retiring instructions, but longer stalls will be called out explicitly. And so in this case then, all of these instructions, all 15 cycles, fit in a single group. And so there are 12 consecutive cycles where we either retire instruction or stall for 1, followed by 3 cycles where we stall for more. And now we have a B token introduced here as well. So the B token is what we call missed opportunities. So in this case, there were 3 cycles where we stalled that were amortized into the A count, but where we didn't retire an instruction. So here we can see over a 12-cycle period, there were 3 missed opportunities, equating to a total of 9 instructions retired over a 12-cycle period, followed by a stall. So in this case, it's a single group of 13 bits, so far more efficient. So we're now down to 1.4 bits per instruction instead of 2 bits. So we've lost a little bit of precision, but if you're mainly interested in the larger stalls, then that's a reasonable trade-off. So what about a CPU a multi-issue CPU that can retire more than 1 instruction at once? So for this case, again, we use the ABC triplet. And here I've modified the diagram slightly to show the number of instructions that retire on each cycle. So we can see the first cycle we retire 1 instruction, the second we retire 4, and so on. So in this case, the first group, you can see there are 4 cycles back to back where we retire instructions, so A is 4. This is a 4-way superscalar CPU, so in theory we could have retired 16 instructions over those 4 cycles. We actually only retired 10. So we've got 6 missed opportunities. That's what's listed in the B token, followed by a single cycle of stall. So we apply the same process for the other 2 groups. So here, we have 29 bits in total, 1.2 bits per instruction. So still pretty efficient. But this might still not be accurate enough for some people. They may actually want to know specifically on a cycle-by-cycle basis how many instructions retired in that cycle. So this is where the DNE token format comes in. So this gives per cycle information. So you can see here, D represents the number of instructions that retired in a particular cycle, and the E is the number of cycles until the next retirement. So a value of E of 1 means you retire on the next cycle, so the gap is 0. A value of 2 means there's a stall of 1, and so on. So here we can see many more groups. We have 9 groups now, but the groups themselves are much smaller. In most cases, the D value is encoded as just a fixed width binary field, although it doesn't have to be because it's bounded. A 4-way superscalar CPU can only retire up to 4 instructions in a cycle. So although we have 9 groups, in fact, it's still pretty efficient, just 1.25 bits per instruction. This gives you the highest precision level that you could hope for. Okay, so just wanted to give an illustration of the algorithm that's used. So this flow diagram is illustrating the basic A and C token case. There are similar. The flow diagrams are similar for the other formats, and I've omitted some boundary conditions for clarity. But so basically, the entry point here is at the top left. So we enter and ask, did an instruction retire on this cycle? Well, if it did, then we check to see whether the C count is 0. So initially it would be. And so we'll drop round to the bottom and out back to the left, increment the A count. And we'll go around that loop, incrementing the A count for every consecutive cycle that we retire an instruction until we encounter a stall cycle. Then it will increment the C count, and it will go around that loop repeatedly until we encounter a retirement again. So at this point, we've now got an A token and a C token. So the C token will now be non-zero. So now we have our group, and we're going to concatenate that into a packet. The trace packet will be a concatenation of groups of numbers up to some limit, the maximum packet size typically. So the first question we ask is, will it fit in the packet? If it will, then we'll concatenate into the packet. and zero the counters and carry on. If it won't fit, we'll send out the existing packet, use this group as the basis of the next packet, and then go around and start iterating around again. Okay, so hopefully it's fairly clear. It's a fairly simple algorithm. I'm now going to pass back over to Gaj, who's going to talk about a more holistic system.
Okay, thanks. So remember, I started off saying it's all about the system. It's not about the core. So how does this trace system work with a CPU-centric trace work within the SoC? So we maintain that what you need is a monitoring infrastructure. And so here we have a typical SoC, very high-level SoC, the diagram of an SoC. And yes, there will be non-RISC-V cores in such systems, and we need to cope with them. So what we say is that what we need is system-wide visibility, which includes things like protocol-aware and transaction-aware bus monitors, embedded logic analyzer. These things can be configured at runtime to provide information like metrics or trace capture or cross-triggering. And then the data that this generates gets transported across a message passing fabric, which is completely orthogonal to the target system, so we're not affecting the behavior of the target system. And then finally, there's something we call communicators, and these communicate the UltraSoC world and another world. So we have some I/O communicators, things like support for USB 3, USB 2 completely in hardware, Aurora. There are people who still use Aurora. And then we have a way of something on chip to be a target CPU to be able to analyze the metrics that, or the information that we generate. There are ways of pouring high bandwidth trace into memory and then pulling out across a smaller pipe. And then we have a bunch of other modules which help with visibility elsewhere. And then what we're working on now is a way of taking that data and providing it to a runtime's analytics system, which does autonomous anomaly detection and then causality as well. And this is very important for things like safety and security systems, but also important for things like where optimization and runtime performance data is required. And then this is where the trace encoder stuff works. This is the CPU-centric information. Some of it's classic run control, but the encoder that Iain is talking about is the one there talking to the RISC-Vs. As you can see, this fits in the whole coherent architecture of the monitoring system. So this is the non-intrusive bit, but as we progress to more and more complex systems like autonomous cars, we're going to have modules that actually provide prevent certain transactions from taking place. And so for that, we have things like the bus sentinel, and then we've also a lockstep monitor, which is not just observing transactions coming out from a CPU subsystem, but it's also observing and tracking the internal states of the CPU. And then in addition to that, we have a way of helping secure areas of the monitoring system which would be initiated by a trusted environment on chip. And then finally, summary. Well, today's system, it's all about systemic complexity. And then understanding today's systems, yesterday's tools is not very easy. So we need to understand how the system is behaving and what impact it has on things like the CPU. And the way to do that is via a non-intrusive monitoring system. And that's what we just shown you. So that's it, folks. Any questions? We've got about 20 seconds.
I have a question about the retirement delta trace. Is it useful on its own? Because it doesn't tell me why a stall happened, right? So unless I correlate it with the actual instruction trace, I don't have any insight into what caused the stall.
Okay, so it will be correlated with the instruction trace. So you need the regular instruction trace to be able to know which instructions those instructions are, and they both come out of the same encoder. So this format is an adjunct to the existing compressed branch trace that would come from the encoder.
How this scheme is very nice, by the way, is comparable to, say, counting, because you may, even on some architectures, ARM, there are counters for, say, stalled and non-stalled, then you have the periodic packets.
Sure.
How does this scheme, if you could address that?
So I think that the difference is that that's more of a statistical analysis. So you'll know how many stalls there were or how long, but you won't necessarily know where they were, which instructions specifically caused them. Yeah, I think it's just a question of accuracy and precision.
Yeah, I mean, yeah, that's like PMU style, but I'm talking about, for example, Cortex-Ms. They have like 8-bit counters, and they have the periodic overlaps. By being sort of precise, you may have a good idea where the CPU is stalling, because as you said, it's usually not stalling on simple instructions, it stalls on some instructions only, right? So that's, but I like the idea anyway.